this section we want to talk about the optimal property of the maximum likelihood estimators. Actually, there are two property which satisfy for the maximum likelihood estimators. First is the invariance property, and second the asymptotic normality distribution of the maximum likelihood estimators. These two property make the maximum likelihood methods popular for especially in the applied statistics. First, talk about the invariant property. If theta hat x is the MLE of the theta, though for any real value function theta, the MLE of theta is given by the theta hat x. In this case, we don't talk about the mathematical form of the theta. It's the only of the function of the theta. So it is very nice property because help the statistician to find the MLE of the any real value function without looking for the form of the function. For example, we want to find the MLE of theta r based on the random sample x1 to xn from density, discrete density function, that one. So let consider first observation is not equal to -1. It is not restricted conditional because the x1 to xn is a random variable or independent of each other, and the change of the order of them is not important. So the likelihood function is given by that form, and the log likelihood is this form. So by solving these equations, we can find the MLE of the theta, which is given by theta hat x equal y minus 2m in n plus m plus sigma I equal 1 to m x power minus 1. Oh, it is simple. For the theta r, the likelihood maximum likelihood estimator given by the theta hat r x is as this form. Is the first property. The second property is the asymptotic normality of the distribution of the theta. Let x1 to xn be a random sample of fx, and theta hat is the MLE of theta. Then, under regularity condition, theta hat has asymptotic normal distribution between theta and the variance is that one. For example, we want to find the distribution, asymptotic distribution of the theta called theta k when x1 to xn is a random sample from in that distribution. The MLE of theta is that one. So the MLE of theta hat is given by this. Now we look for the variance of this estimator. ln fx is equal to ln theta minus 1 plus theta ln 1 plus x, and get, if you look for the derivative of the ln of log of fxi respect to theta, we can find this value, and second derivative given by minus 1 and over theta square. So we can find derivative of 2 theta with respect to theta, and the variance given by theta square over n theta 2 to k. So the estimated theta at the kx is given by, has a distribution, normal distribution, asymptotic normal distribution as follows. In the multi-parameter cases, let x1 to xn be a random sample from fx theta, where theta is theta 1 to theta k, and theta hat x theta 1 hat 2 theta k hat the MLE of theta, and the regularity condition theta hat x has asymptotic normal, multivariate normal with mean theta, and covariance matrix that one. For example, let x1 to xn be a random sample from normal theta 1 and theta 2, and we look of the asymptotic distribution of the maximum likelihood estimator of theta 1 and theta 2. First, we know the maximum likelihood estimator of the theta 1 is equal to x bar, and for theta 2 is equal 1 over n sigma I equal 1 to xi minus bar square. So we look for the logarithm of fx has this form, and the derivative of the logarithm of x with respect to theta 1 is given that, and with respect to theta 1 square is that one. The second derivative is this second derivative with respect to theta 1 and theta 2 given of that, and derivative, first derivative as second derivative log fx is that one. So we have expectation x minus theta 1 equals 0. This is theta 2, and expected x minus theta 1 square is theta 2 because it's the variance. Therefore we can calculate the expectation of second derivative with respect to theta 1, and with expectation is minus expectation x minus theta 1, which is 0, and so the second derivative of log fx with respect to theta 1 theta 2 is 0, and the expectation of second derivative with respect to theta 2 is that one, and you can find the variance covariance matrix as that. So this said the theta 1 and theta 2 are independent and has normal distribution, theta 1 hat or x bar theta 1 and theta 2 over n, and second one is normal theta 2 and 2 theta 2 square over n. If you look at x bar actually has normal distribution with mean theta 1 and theta 2 square over n, but the second one actually has the chi-square distribution, which n degree of freedom. If you look at the asymptotic distribution, the asymptotic distribution and this reality distribution is the same, but for the theta 2 the in actual distribution is chi-square with n degree of freedom, but the for n minus 1 degree of freedom, and but the asymptotic distribution is the normal distribution. So another point which should consider in a MLE estimator is it's actually is the good point estimation, but because have some optimal property, but there are some drawback problem, because when you look for the maximum of the likelihood function, it is a mathematical job. However, finding the global maximum and verify this global has sometimes very difficult. And sometimes we need the iterative methods to find the maximum likelihood estimators. Actually, if the derivative with respect to theta are not linear function of theta, finding the MLE is very difficult. If you look of the, we have we have solved this derivative, these equations, to find the MLE of theta j, but if they aren't simple for mathematical for we have some difficulty. We need to use some software to find the maximum likelihood estimator. Actually, in the all statistical software we can find methods to obtain the maximum of the mathematical function, but the theoretical form for the simple method can be used. So, for example, here find example such is the such that show the difficulty of the method of maximum likelihood estimator. Let's x1 to xn be random sample from this density function. We want to find the MLE of theta and alpha. The likelihood function is given by that one. So this is decreasing function of alpha for fixed theta. So the MLE of the theta, which make that likelihood function maximum, is that alpha is equal xn minus 1. So because the likelihood function has two parts. It's the first part, it's the second part. This is the indicator function, is take values 0 and 1. The maximum is when this indicator function take value 1. So the alpha hat should be in this interval. However, if look of the here, we find for the fixed theta, L theta and alpha is a decreasing function. So in this case, if we want to take this maximum and this maximum, first alpha hat should be in this interval, but if you look of this function, because it is a decreasing function of alpha, then should be alpha take the minimum value of that as here. If put here alpha hat in this likelihood function, we have the likelihood function only for theta. If you look at that, we found L theta is the differentiable function respected to theta, so we can use the derivative methods. Here first we take log likelihood, and second we take the derivative of log likelihood. But if you find that one, we find a very complicated function of theta. It's not the simple one. So the value of theta, which is MLE, is the root of this equation. Okay, because is solving this equation is meaning the likelihood MLE, the likelihood maximum likelihood estimator, is the root of this equation. If look of this equation function chi theta, we found if theta tends to 0, chi theta tends to infinity, and if theta tends to infinity, chi theta tends to value that one which is negative. So the function of theta, the function of chi theta is a decreasing function of theta, and in the 0 it is positive, and in the infinity it is negative. So the equation chi theta equals 0 has one unique solution. We want to find it. Let have ln xi less than ln1 plus alpha hat, which is ln xn. It is very simple, because the xn is the n order statistic, which is the maximum value of xi. So the ln, all xi less than xn, and we can take ln as two non-equality, two side of non-equality, and so we have sigma I from 1 to n ln xi less than n ln 1 plus alpha hat. Therefore the round theta, chi theta with respect to round theta, or the derivative of chi theta is negative. So chi theta is the strictly decreasing function of theta. So this has a unique solution, and we need the numerical method to solve this equation. We only prove the equation chi theta equal 0 has unique solution, because when you want to use the numerical method, we be sure that this equation has solution, and then we use the numerical methods. In example 3.12 is another problem with the Emily methods. Let x1 to xn be random sample from beta distribution, rho theta and 1. The Emily, we want to look for the Emily of theta and rho as well. The log likelihood is that one, and the derivative of the log likelihood given by these equations. And when you look for the derivative, the solving a derivative, we can find only one equation. So we have two unknown parameters and only have one equation. So in this case, the Emily of theta and rho does not find, and we say the Emily of theta and rho are not identified. For more details, you can see that academy 22.2008. So the maximum likelihood estimator is the simple methods to find the point estimators and has some optimal property. Actually, we should be look for this problem. Two of problem. One problem is it is possible to need the numerical method to find it, is not theoretical methods, only theoretical method to find the Emily estimator. It is possible to other method has this problem. And second one, sometimes maybe the Emily of theta is not identifiable and we can find it, but the method is the make the function maximum. This is a technique, mathematical techniques, and in the some software or some books have talk about the finding the mathematic in maximum of the mathematic functions. So but the very nice property of maximum likelihood make it very popular to use by the people, especially in the applied statistics. Okay, because in the applied statistics the form of the maximum likelihood estimator is very complicated, and we cannot find the density of the maximum likelihood estimator to make statistical inference, for example confidence interval or testing hypothesis. So the people use the maximum likelihood, because if they can't find the actual density function of the maximum likelihood, we can use the asymptotic distribution, which is normal, no asymptotic normal distribution. And as we know, we can find tables of the value of the normal distribution, and it is very simple to use the normal distribution in the finding confidence interval or testing hypothesis. In the second point, there are problems. Sometimes it's easy to find it. The maximum likelihood is by the derivative, but second, it needs some discussion, and sometimes it needs numerical, and sometimes we haven't maximum likelihood estimators. Good luck.